Well, hello everyone. Right now we're going to be going over the many different types of organic compounds. And first we're going to be starting with alcohols. An alcohol is an organic compound with a hydroxyl functional group, which is just a fancy way of saying one of the hydrogens has been replaced with an OH group. They're non-electrolytes and they don't really change colors and indicators. Now, when it comes to naming an alcohol, you have to cite the location of the OH group, which means what carbon is it attached to, and then you replace the E with an OL ending. Hence, right here up top with this example, you have propanol instead of propane. And to draw one of these out, the written structure has it on the last part. So you draw your three carbons from pro, and then you attach your OH to the end, and then you draw out all of your hydrogens. And this is the structure of one propanol. Now you could have also put it on this carbon because it also signifies a one spot, but you can't put it here in the middle. That's a two spot. So that's alcohol. A halide is a hydrocarbon with a halogen functional group. So that would mean one or more hydrogen is replaced with either fluorine, chlorine, bromine, or iodine. Multiple halogens can be used, and you can have one or more halogen within that halide. So in order to write out a halide, you have to cite the number of halogens, you have to cite which ones they are, and you have to cite where they are. So for this example, 2-chloropropane, that means you have a chlorine at the second carbon. And since it's chloro, that means that there's only one chlorine. If it was 2, it would be dichloro. If it would be 3, it would be trichloro, and so on and so forth. So you have your 3 carbons since it's pro, and you have your chlorine on the second. It really doesn't matter if it's above or below, it just matters that it's on that second carbon. And you just draw out the rest of your hydrogens. And there you go. Now you have the structural drawing of 2-chloropropane. So alcohols start to get a bit tricky because there are many different types. First, you have primary alcohols, in which in a group of carbons, you have the OH group on one of the ends, which are your primary carbons. For secondary, in your group of carbons, it's usually one of the middle groups that would have the OH, and that would be your secondary alcohol. And for your tertiary, it's usually not in linear groups, but it's more or less in branched groups. And right here is where you would have your tertiary carbon is to make your tertiary alcohol. Now, you also have dioxy and trioxy alcohols, which are just fancy ways of saying one has two alcohols in the group and the other has three OHs in the group. At first it'll start to seem confusing, but once you get some examples going, it starts to get easier. An ether is an organic compound where instead of just constantly bonded carbons, you have a carbon attached to an oxygen attached to a carbon. So it's technically two separate carbon chains that are bonded together with an oxygen in the middle. So in order to name a ether, you have to name the first part in accordance to the number of carbons in the first part before the oxygen. Then you have to name the second part, and then you end it with ether. So for methyl ether, you have one carbon before the bonded oxygen and two carbons after the bonded oxygen. And to draw that, you would have your carbon, then your oxygen, then your two other carbons past it, and then you draw all your hydrogens. And that will give you the structural drawing of methyl, ethyl, ether. An aldehyde is an organic compound with a double bonded oxygen attached to one of the end carbons within the group. So for this example here, propanol, you can't have the double bonded oxygen in the middle carbon. It could either be on the first carbon or where it would usually be the last carbon. So for this structure, you would, as it is pro, you would have three carbons, and you would have the double bonded oxygen, and then you would just have your hydrogens. And there you have propanol. And with it being now, you see that all you have to do is replace the E with an AL ending. So that is how aldehydes are supposed to structurally look, and that's how you name them. Now, a ketone is an organic compound with a double bonded oxygen attached to any of the middle carbons, not to get confused with an aldehyde where the double bonded oxygen can only be on one of the end carbons. This is one of the main things that sets aldehydes and ketones apart from each other. They're both called carbonyl groups. Their functional groups are both called carbonyl groups, but the placement of the carbonyl group determines whether it is a ketone or an aldehyde. So here, for 2-pentanone, that means the double bonded oxygen is on the second carbon. So you have 5 carbons since it's pentanone. So your double bonded oxygen can either be here or it could be here, because that's one of the areas where the two could possibly be. So we're going to put it at the beginning too, and then you just put in the rest of your hydrogens as per usual, and you have the structural drawing of 2-pentanone. And notice the ending. Once you establish where exactly the double bonded carbon is, you replace the E with an ONE ending. So instead of pentane, it's pentanone. An organic acid is an organic compound with usually what seems to be only a slightly acidic characteristic. And it has what is called a carboxyl group, which is pretty much part of an aldehyde and an alcohol. Those two functional groups put together, and that's where an organic acid functional group seems to be. So it's pretty much adding those two together, and you have a carboxyl group. Now, when you name these, all you have to do is replace the E with an oic acid ending. And since they're at the end, because you have to have that ending OH, it's not going to be like 2-propanoic acid or something crazy like that. And to just draw one of these out, so you have your 3 carbons, you have your double bonded oxygen, and you have your OH at the end. And then put in your hydrogens. And we have now just drawn propanoic acid. An ester is sort of similar to an ether in the sense that the name is broken up into 2 parts. It's an organic compound in which the functional group is really derived part from an organic acid, part from an alcohol. And esters usually have very pleasant smells. That's why most perfumes and colognes are usually esters. To name an ester, you have to cite the first half, then you have to cite the second half, similar to an ether, but instead of ending with the word ester, you would instead replace the E ending with an OH ending. So methyl, 1 carbon, pro, 3 carbons, and then your OH ending. So you have your 1 carbon for the methyl part, and then you start your propanoate part here. 2 hydrogens, then you have your second carbon, double bonded, single bond, last carbon. And then you put in all your hydrogens. And that is how you get methylpropanoate. An amine is an organic compound, which is basically the derivative of ammonia, in which you replace the H's with alkyl groups, which are either CH3 or CH2. Because it can start out pretty simple and then it just turns H into CH3 and so on and so forth until you have all these very, very long amines. So to name an amine, all you have to do is simply replace the E with an amine ending. And drawing these out is relatively simple. Now, as you can see, we have one propanamine. And in the written form, your nitrogen is at the end. So you have carbon, carbon, carbon from pro, and then you have your nitrogen bonded at the end. Now, your nitrogen is only bonding to two hydrogens, and the rest is just carbons and hydrogens. This is because nitrogens can sustain stability with only 3 bonds instead of 4. And that is how you draw 1-propanamine. There we go. An amide is a organic compound that is the product of a combination of 2 amino acids, and these are usually very long chains, and they're held together by what is called peptide bonding. Now, these are very these can look very similar to amines because the functional group is quite similar, but what you notice here is one, you have a carbon already in the functional group, and you have a double bonded oxygen. Amine has no double bonded oxygen. So if you see nitrogen and a double bonded oxygen, that's how you can tell that it's an amide instead of an amine. An isomer is an organic compound that can have more than one structural arrangement. So, for example, up here you have C4H10 broken down into 2 ways. One way you have butane, linear, your 4 carbons straight across all your hydrogens. And on the other side, you have 2-methylpropane, which has 3 carbons, with the second yielding a single carbon chain. Now, they may all be single bonded, they may all have the same number of carbons and hydrogens, but at this point, they have different physical properties based on their structures. For one, their boiling points are different because their polarities are different. This is a non-polar molecule. This is a polar molecule. Symmetrical, asymmetrical. Their melting and boiling points are different. And when you come to have isomers, one isomer is going to have different physical and chemical properties than another one. And one more thing about isomers is that as the complexity of the hydrocarbon increases, the number of isomers goes up. So right here you have CH5H12, and you only have 3 isomers. Okay, that's pretty manageable. And then you get to eventually C8H18, and you get 18 isomers. Now we're starting to get a lot. And then it goes all the way until you get, and we're stopping really at a very, very simple number at this point, because you can go on and on forever. C20H42, and that yields 366,319 isomers. So there are over 300,000 different shapes for this one formula. So as the complexity of these hydrocarbons increase, there's more ways to fit them in, and there's more ways to structurally draw them. And each one of these isomers has different physical and chemical properties from the other.